Good morning. Welcome you all to this session of fluid mechanics. Okay, in the last class we were discussing the concept of specific energy in a channel flow. Just if we recall, the specific energy at any section in the flow through an open channel was defined as the total mechanical energy at that section, where the potential energy was taken from the base or the bed of the channel as the datum, and the expression of specific energy, if you see, was like that: Es is equal to H plus V square by 2G. H is the depth of flow, and then this V was substituted in terms of Q. This Q is the flow rate per unit width of the channel. So this was the expression, and then we considered that for a given flow or discharge Q per unit width, the variation of the specific energy Es with the depth of the channel like this. This was discussed in the earlier class, the last class. And this curve distinctly shows a minimum value of the specific energy for a given H depth of the flow, which is termed as critical depth of the flow. Now our next point, or the next task, is to find out the value of this minimum specific energy, or this depth known as critical depth, at which the specific energy becomes minimum. So that can be found by differentiating this expression. Let us write the expression now again. Es is equal to H plus 1 by 2G Q by H whole square. Now for a given discharge rate, Es will be minimum for a depth which can be found out if we differentiate del Es del H and set it to 0, which will be 1 minus Q square by H to the power minus 2 G H cube, and that should be set to 0. Okay, if this is made 0, then we get Q is equal to GH cube to the power half. So this is the relationship between the flow rate with the depth H. Now this H can be expressed as HC, so we can tell Q is equal to G into HC cube whole to the power half. Or we can write HC as the Q square by G whole to the power 2/3. So this is the relationship given. Now if we express this Q, substitute this Q in terms of HC here, we get the value of the minimum specific energy. Okay? So minimum specific energy will occur at critical depth HC, and at that condition the flow rate is given by the expression GHC whole cube to the power half. That means Q square is equal to GHC cube. That means GHC cube. So Q square is GHC cube divided by HC. So GG cancels, HC cancels. So this will be 1 plus half. That means 3 by 2 HC. That means we get Es minimum is equal to 3 by 2 HC. Okay, and Q, corresponding Q, is GHC cube to the power half, or HC can be written as Q square by G to the power 2/3, and this can be written, the critical depth in terms of the minimum specific energy is 2 by 3 Es minimum. So these are the outcomes that for the minimum specific energy for a given discharge. Now if we focus our attention in a different direction from this equation, if you consider that if specific energy remains constant, what is the variation of H with Q? Now you see, in this case we can write Q square. If I write it again, okay, Es is equal to H plus 1 by 2G Q by H whole square. So you can write Q square is equal to 2G Es minus H into H square. Now you see, when H is equal to 0, Q is 0. Now here also Q varies in a fashion that it may increase with the increase in H or may decrease with the increase in H. This is because H happens here, which produces a decrease in Q with its increase. Again, this H produces an increase in Q with its increase. And one thing is clear, that Q is equal to 0 when H is equal to 0, and again when H is equal to Es by magnitude, then Q is also 0. So this relationship gives a curve like this. That means if we draw a curve of Q versus H, depth versus Q, for a given value of specific energy, const minimum the specific energy, then we get a curve like this. we get a curve like this. So this is the Q versus H curve. So this curve shows clearly a maximum. The curve for constant Q, that means this curve Es versus H showed a minimum, and that is mathematically proved that if we make a second derivative, this will be positive. That means this has got a minimum. That means this has got a minimum. That means H versus Es for a given Q. But H versus Q for a given Es has a maximum. Now the depth where it is maximum is the critical depth, and similarly the values of this maximum flow rate is known as Q maximum. So let us find out again what is this condition, or what is this critical depth in this situation, and what is the value of Q max. How to find out? We differentiate this expression with respect to H. That means if we differentiate this expression with respect to H for a given Es, that is the specific energy, we get 2Q del Q del H is equal to 2G, then 2G, 2 ESH, that means 2 ESH, the differentiation of this term, minus H cube 3H square, and that is set to 0, which means that Es into H is equal to 2 ESH is equal to 3H square. So we get Es is equal to 3 by 2H. So you see we get Es is equal to 3 by 2H, and earlier also we got Es minimum is equal to 3 by 2 Hc, and here H is Hc, so Hc. So now if I put this expression here to get the value of Q, so Q maximum square is 2G, so Es is 3 by 2 Hc minus Hc into Hc square. That means we get 3 by 2 minus 1 half, so it is GHCQ. So Q max is equal to again GHC whole to the power 3 by 2. So we see that at critical depth HC, when the Q is maximum, discharge rate is maximum, the maximum discharge rate is given by GHC to the power 3 by 2. And at that condition, the specific energy is 3 by 2 Hc. And at the same time, if you compare these results now, at the minimum specific energy condition with a given discharge, Q is given by this expression, Es minimum is given by this expression. So if you compare these two with these two, then we can conclude that at the critical depth Hc, either discharge rate is maximum when specific energy is kept constant, or the specific energy is minimum when the discharge rate is kept constant. So therefore critical condition is a condition corresponding to a critical depth Hc where the specific energy is minimum for a given discharge, or discharge is maximum for a given specific energy. Okay. Now after this we will try to find out what is meant by alternative depth and different regimes of flow, tranquil and rapid flow. Tranquil and rapid flow, and concept of alternative depth, concept of alternative depth. Okay, now let us reveal again the two curves. One is Es versus H, that is H versus Es for a given Q. The graph is like this. If you recall, the graph is like this. That means this is the minimum, this is the Hc, this is the Hc. This corresponds to the minimum Es minimum. And if you draw the graph of H versus Q for a given, here Q is constant, and for a given Es, let Es is constant, we get a curve like this. So this is the Hc here, Hc. So this is the Hc and this is the Q max. Now we see in this curve here, at any specific energy, there is, for a given Q, there are two depths of flow. One, if you consider as H2, another can be considered as H1. So there are two depths of flow. One is higher than Hc, that is H1, one is lower than Hc. One is this side of this maximum point, another is this side of the maximum point. Same is valid true here, that for a given specific energy and for a given discharge rate, there are two depths. One is H1, which is greater than Hc, another is H2, that is H2, which is less than Hc. These two depths are known as alternative depths. Now when H1 is greater than Hc, V will be less than Vc. And when H1 means H I am writing now in terms of H greater than Hc, that is the case with H1, then V, the corresponding flow velocity in the channel, will be less than the critical velocity. When H is less than Hc, obviously the flow velocity will be greater than the Vc. Okay? So Vc is the critical velocity, Vc is the critical velocity, Vc is the critical velocity. How do you find out the critical velocity? You know Q is equal to GHc cube to the power half. So Q square is GHc cube. What is Q? Q is V into H. So Q square is V square into H square, and here I put critical depth H square is equal to GHc cube. So V square is simply equal to GHc. This is the V square. So V is equal to root over GHc. So therefore we see this, the flow velocity V is less than the critical velocity. So this is V when H is greater than Hc. So when H is greater than Hc, V, again I am writing V is less than Vc. Vc is what? Vc is root over GHc. And when H is less than Hc, V is greater than Vc, that is root over GHc. Now, before specifying the two regimes of flow, we should know what is the physical implication of these two. What is the physical implication of these two? Now, if we recall earlier discussion that in a channel, if there is a flow and if a disturbance is created at downstream, so disturbance moves upstream with a velocity c such that if this velocity is v, the undisturbed velocity of the channel flow, because of the disturbance passing through this channel flow, the downstream section, the height will increase and velocity will change. But we refer the condition of the hydrodynamic parameter of the channel as the undisturbed velocity of flow v here in the upstream. So we know that the v plus c is equal to gh to the power half. That means this disturbance waves propagates upstream with a velocity which is gh to the power half relative to the flow velocity of the channel. So actual velocity, absolute velocity of propagation of the disturbing wave is therefore gh to the power half minus v, that is the flow velocity of the channel. Now this v, when v less than vc, that means when v less than root over gh, that is the case when h greater than hc, then c is positive, c is greater than 0. That means there is a possibility, all possibility that this disturbing wave reaches the upstream and changes the condition in the upstream. But when h is less than hc and v is greater than vc, that is v is greater than root over gh, then in that case c is less than 0, c becomes negative, which means that c is negative means the propagation wave cannot propagate, or the disturbing wave cannot propagate or proceed in the upstream direction. So in this regime of flow, any disturbance created in the downstream cannot propagate upstream. So this is very important physical implication. So the case when v is equal to vc is equal to root over gh, then this propagation, absolute velocity of propagation of this disturbing wave becomes 0. This is equal to this 0. In that case, if you create a disturbance somewhere, this will create a wave which neither moves in upstream direction nor moves in downstream direction. This is the case known as standing wave. That means in a critical flow situation, the disturbance creates a standing wave. In other situation, the disturbance creates a wave which either can propagate in upstream when h is greater than hc and v is less than vc, or it will not propagate in the upstream when h is less than hc, that is the critical depth, and the velocity of flow is greater than the Vc, velocity or critical velocity. Now we again see that when V is less than Vc, that is the depth of flow is greater than Hc, this is the case, the disturbance wave propagates upstream. In that case, if we define Froude number, we can write V, if you recall, is root over GH. And in this case, Froude number is less than 1. So I write everything for this case. The disturbance wave propagates upstream. Wave propagates upstream. Okay. And another situation when H less than critical condition and V is greater than Vc, then Froude number is equal to V by root over GH become greater than 1. And in that case, disturbance wave doesn't propagate upstream, does not propagate upstream. And this regime of flow is known as tranquil flow, where the flow velocity is less than the critical velocity and the depth of flow is greater than the critical depth of flow, and disturbance wave propagates upstream. And this flow is known as the rapid flow, where the flow velocity is greater than the critical flow velocity and the depth of flow is less than the critical depth of flow and Froude number greater than 1, and disturbance wave does not propagate upstream. These are the two regimes of the flow. All right. So next, after this, we will go to the concept of hydraulic jump. After recognizing these two types of flow, tranquil and rapid flow, we will consider the hydraulic jump. So by definition, hydraulic jump is a transition. Hydraulic jump, by definition, we can define hydraulic jump as a transition which takes place when a rapid flow is suddenly decelerated to a tranquil flow. Now, we have to know under what situations rapid flow occurs in practice. Rapid flow occurs in practice when water is released at high velocity under the sluice gate or at the foot of a spillway. Now, if this flow is decelerated by, for example, by the roughness of the bed of a long channel, or by putting some obstruction on the downstream, if a rapid flow, that means a high velocity flow where the velocity of flow more than the critical velocity is suddenly decelerated to tranquil flow, if the type of obstruction or resistance is such that it has to decelerate to tranquil flow, then the deceleration takes place very suddenly and in an irreversible manner, and the sudden irreversible transition is known as the hydraulic jump. Now let us find out or investigate the hydraulic jump in detail. Now if we see this again, this H versus why it happens so, ES, now the curve is like this. Okay, so this is the minimum point and this is the critical point. Let us define this as C, and this is HC, and this corresponds to minimum. Now we are with the definition we know this is the tranquil flow regime. Where the depth of flow is higher than the critical flow, and this is the rapid flow regime. Now you see, if a flow is in the rapid flow regime and if it is gradually decelerated by the action of friction or any resistance, the same thing, resistance means it produces friction in the flow, so that the flow is decelerated. Now if it has to follow the usual depth versus specific energy curve, now you see that it cannot go via the critical section and then go to tranquil flow. Why? If it goes to the critical section in the rapid flow regime, we see that specific energy decreases with the depth. That means the depth is increasing, the flow is decelerated, velocity is decreased and depth is increased, and specific energy also decreases. But when it reaches critical flow, that's critical flow at this point here, then it has to, if it has to follow this path to go to the tranquil flow, then you see what happens with the deceleration, its specific energy should increase, which violates the law of conservation of energy, because without the addition of energy from outside, the flow cannot be decelerated to tranquil flow from the critical condition with the addition or increase in the specific energy. So it cannot follow the path like this. That means the rapid flow cannot be decelerated to tranquil flow via the critical conditions, that means along this curve. So the only alternative is that at some location here, a rapid flow, for example here, suddenly goes transition to the
tranquil flow, which shows a decrease in energy, not via this path. So this path is an irreversible path shown by a dotted line. Let this is the point 1 in the rapid flow regime, let this is the point 2 in the tranquil flow regime. So this from 1 to 2 it goes by irreversible path. This is a sudden transition, during which there is a loss of specific energy. This loss of specific energy is termed as HJ, that is head loss, the loss of total energy per unit weight, head loss in the jump, that means hydraulic jump. So therefore this is the way by which a rapid flow is decelerated or converted into tranquil flow. All right. Now this phenomena is known as hydraulic jump. Now we will first find out what is the relationship between these two depths, that is the depth in the rapid flow and the tranquil flow in a hydraulic jump, and then we will find out what is the head loss in the hydraulic jump. Now if you remember that we derived some equation regarding the depth of flow and the velocity while deriving the velocity of propagation of the disturbance wave, you will remember the disturbance wave will propagate. If we now give the velocity v1, then we can write gh2, if you recollect, to the power half into 1 plus h2 by h1 by 2, this to the power half. So this is the expression which we develop when there is a disturbance wave propagates in a channel where the downstream depth is h2, which is an increased depth from that of the upstream undisturbed depth h1. This is the similar situation because the downstream depth in case of a hydraulic jump it corresponds to a higher one as compared to the upstream depth. This is because the flow is decelerated from a rapid to a tranquil one. So if we use this equation, if we remember this v1, not v1, it was there c plus v1, I am sorry. If we put now c is equal to 0, why we put c is equal to 0? This is because in a hydraulic jump, we can draw it here. So if we consider a hydraulic jump, if we just show a hydraulic jump in a channel like this, that it is a rapid flow with a lower depth, this h lower than hc. So it suddenly goes through with a sudden discontinuity in the flow field, suddenly transferred to a tranquil flow, where this h, let this is the h1 and this is the h2, this corresponds to tranquil fluid which is greater than hc. So this discontinuity takes place through a standing wave. So in that case we can consider this rapid transition through this, so this point to this path, where the usual depth versus specific energy relationship does not hold good. So this doesn't come along this path. We have just described that. So this transition can be conceived as a form of a standing pressure wave through which the flow passes, so that it is decelerated, its depth is increased and the flow velocity is decreased. So as a form of a standing wave where this transition takes place. So this transition is not a moving transition, it takes place at a particular location. So this can be made similar, or it can be made analogous to the disturbance wave which is moving through a channel with 0 velocity, so that in mathematical analysis we can make c 0. So we get v1 is equal to gh2. Now if we square it, making c 0, make it square, so it is gh2 into h1 plus h2. So if this 2 I take here, 2 and this h1, v1 square, 2, so you square it, gh2 v1 square h1. So we can write now h2 square, so g here, so we can write h2 square plus h1 h2 minus 2 v1 square by g, v1 square h1 by g is equal to 2 v1 square h1 by g, h2 square plus h1 h2 is equal to 0. Now flow velocity v1 can be written as, what is v1? v1 is q by h, where q is the flow rate per unit width. So if we replace this, we get h2 square plus h1 h2 minus 2 q square, so h square, that means gh1 is 0, or simply we can write h2 square h1 plus h1 square h2 H2 square H1 plus H1 square H2 minus 2Q square by G is equal to 0. Now this is an equation which is symmetric with respect to H1 and H2. So if we consider this equation as a quadratic equation in H2, then we can do one thing, we can find out the root of H2. What is H2 then? This will be minus H1 square plus minus root over, this is B square minus, then this square, this means H1 fourth, this is minus, so plus 8 for this into this, Q square H1 for Q square by Q square H1 by G. 8 Q square by G into, that is H2 square, so H1 4AC divided by 2H1. So this is the root of this equation to find out the value of H2. So H2 will give. So we can neglect this minus sign because it is minus, so negative root is physically impossible, the depth cannot be negative, so therefore we take only the positive root, so we get H2 is equal to, so if we take the minus H1 by 2, then we can write plus, then if I take H1 square common, so H1, so plus, so or we can write within the square root rather 4H1 squared, so we can take H1 square by 4 plus what we can write 8Q square, so not 8Q square, 4 will be inside, so 2Q square by GH1, this to the this, okay, the same thing we can write to the power half. H1 square by 4, that means I am taking this 4 inside this, so we get 2Q square by GH1, because H1 square will be there, so GH1 whole to the power half. So this is the value of H2 in terms of H1. So we can get also the value of H1 in terms of H2, we just simply change the suffix. This is because this equation is symmetrical with respect to H1 and H2. So this can be written as H2, as if we take common H1 by 2, we can take H1 by 2 common, and then we can write this expression as minus 1 plus minus 1, H1 by 2 we are taking common, 1 plus 8Q square, that means I am taking H1 square by 4 as common. So H1 square by 4 as common, so H1 square comes in the denominator, so GH1Q, this is whole to the power half. Now again we know that this Q is equal to what? Q is equal to V1 into H1. So if we put Q is equal to V1 H1, this term will become 8 V1 square H1 square by GH1Q. So 8 V1 square by GH1. So V1 square by GH1 square is Froude number 1 square. So V1 by root over GH1 is the Froude number. So we can write H2 by H1, making this side in dimensionless term half into minus 1 plus minus 1 plus 8 Froude number, FR1, Froude number corresponding to the upstream condition, Froude number square, I am sorry, whole to the power half. So H2 by H1 half, 1 plus 8 Froude number square minus 1. So this is the final expression for the ratio of the two depths. So H2 is the depth corresponding to the tranquil flow when it is decelerated. H1 is the initial depth of flow for the rapid flow. This is equal to half minus 1. So Froude number 1 is always greater than less than 1. Froude number 2, that means the corresponding to the tranquil flow, or sorry, rapid flow, sorry, Froude number 1, that is FR1, that is the Froude number corresponding to the rapid flow is always less than 1, and Froude number at corresponding to the 2, the tranquil flow, is always greater than 1. So this is the corresponding relationship between H2 and H1. Now we will find out what is the loss of head in the hydraulic jump. That means now we want to find out what is this value, this H1 and H2. So this is the head loss in the jump. So we can find out H1 minus H2. Hj is H1 minus H2. That means not H1 minus H2, I am very sorry. This is the ES1 minus ES2 or ES2 minus ES1. ES1 is more than ES2 because it is a deceleration and loss of energy. You see here also ES1 minus ES2. So I am sorry, ES1 minus ES2. That means we can write, we know the expression of ES, that H plus V2 square by 2. So let us write like this way, H1 plus V1 square by 2 minus H2 minus V2 square by 2. So this can be written as H1 minus H2 plus V1 square minus V2 square by 2. Now this V1 square minus V2 square can be written, you know that V1 is equal to Q by H1 and V2 is equal to Q by H2. So we can write H1 minus H2 plus Q by H1, so Q square, so this will be 2G per unit weight. So Q square by 2G into 1 by H1 square minus 1 by H2 square. Now this Q square by 2G just now we have derived can be expressed, you see here. So Q square by 2G can be expressed from here. That means if we see like this, that Q square by 2G here, you see the earlier one which we derived, that Q square 2Q square by G is this one. So we can write from here Q square by 2G, that means divided it by 4 is equal to this quantity, that is H2 square H1 plus H1 square H2 by 4. That means we can write from here Q square by 2G H2 square H1 plus H1 square H2 by 4. So if we write that H1 minus H2 plus this thing is this H2 square H1 plus H1 square H2, it is easy to remember, by 4 times 1 by H1 square minus 1 by H2. If you make a simplification of that, you get H2 minus H1 whole cube by 4 H1 H2, and this is precisely the head loss or loss of energy per unit weight in a hydraulic jump. So therefore we conclude that when a rapid flow is suddenly decelerated due to some obstruction in the flow field or by the friction in the channel bed to tranquil flow, the conversion or the change in the regime of the flow takes place through a sudden transition known as hydraulic jump. So therefore the rapid flow doesn't go to the tranquil regime via the critical flow. So the critical flow doesn't occur due to the change of the from rapid flow to the tranquil flow. But on the other hand, if a tranquil flow is suddenly accelerated to rapid flow, then the flow passes through the critical condition. That means transition from rapid flow to tranquil flow, that is the flow deceleration, gives rise to hydraulic jump, and the flow doesn't go through the critical flow. So the occurrence of critical condition doesn't take place here, but the occurrence of critical condition takes place when the flow is accelerated from the tranquil to the rapid flow region, because the specific energy and depth of flow relationship is not invalid here. That means it obeys all the physical laws that governs the flow. So therefore here we see that when a tranquil flow is accelerated to rapid flow, the occurrence of critical condition takes place. So under what practical conditions this happens? When the flow from a long prismatic channel with a mild slope approaches to a long channel of steep slope where the flow is accelerated, and therefore flow is acted by an additional gravity force. The gravity force is increased. In that case, the critical condition occurs. Another case is that if the flow flows through a channel with a rise in bed or over a spillway, the tranquil flow is accelerated to rapid flow, and the occurrence of the critical condition takes place at the juncture where the flow geometry is changed. Let us consider the case like this. I tell you the occurrence of critical conditions occurrence of critical condition. Occurrence of critical conditions. Occurrence of critical condition when the flow is taking place through a mild slope to a like this. When the liquid flows like that, then what happens? A tranquil flow suddenly changes to a rapid flow. Here the flow is tranquil, here the flow is rapid. And the critical condition takes place at this juncture, that is the critical condition. Sometimes it happens in practice that if the slope is too steep, slope of this channel, or there is an abrupt change in the slope takes place, then there is an appreciable curvature of the streamline near the junction, the near vicinity of the junction, where the assumption of the hydrostatic pressure variation is not justified. And in that case, the critical conditions may occur little upstream from this junction, somewhere here. Another condition is that if there is a rise in the bed of the channel, so the flow which is tranquil initially may goes to a rapid flow. So this is a rapid flow, and this is the so a conversion from tranquil to rapid flow gives the occurrence of the critical flow, means the flow is critical at that juncture. The flow passes through a critical condition. So occurrence of critical flow occurs. Occurrence of critical flow takes place when the tranquil flow is accelerated to rapid flow, but not the reverse. The rapid flow is decelerated to tranquil flow. All right. Now, next I will discuss the flow of fluids. Flow of fluids through conduits. Through conduits, partly full. The flow of fluids through conduits, partly full. Now, we have seen in many practical, it is found in many practical purposes or in practice that the liquid flows through a conduit partly full. That means it is not full flow of liquid through the conduit. In this case, the liquid has a free surface and the flow is governed by the principles of channel flow. That is the flow through a conduit with partly full, partly filled. The conduit is not filled totally and the liquid has a free surface. So principle is governed by that of the channel flow. Let us consider a circular conduit. Now let us consider such flow through a circular conduit. And let this is the center, let this is the surface of the fluid which is flowing to surface. This is the cross section of the conduit, it is a circular conduit. And let the free surface subtends an angle 2 theta at the center. Let this is center C. So this angle is theta. And let diameter D is the diameter of this circular conduit. Then we can write that what is the cross-sectional area of the flow. So cross-sectional area of the flow is this cross-section. So this cross-section can be written as this. So pi d square by 8 is the half circle, which is the cross-section when this included angle, that means the angle subtended by this arc is 2 theta at the center, when this becomes 180 degree, that is pi. So 2 theta by pi, so correspondingly it is reduced, so that we can make it a simple school level geometry. So d square theta by 4. So d square theta by 4 is the cross-sectional area of the pipe. So this cross-sectional area of the flow is d square theta by 4 minus, now d square theta by 4 is this area. So this is also theta, so this area. So from there we have to subtract these two triangles. So if this is, so how to find out? So this is d by 2. So this, if this is theta, so this is d by 2 sine theta. So this is d by 2 and this is d by 2 cos theta, because this is d by 2. So this is d by 2 sine theta, this is d by 2. So here also this is d by 2 sine theta, because this is d by 2 and this is d by 2 cos theta. That means the area of the two triangles, that means 2 into half d by 2 sine theta, well, into d by 2 cos theta. All right, d by 2 sine theta into d by 2 cos theta, which can be written as A is equal to d square by 4 if you take common theta minus half sine 2 theta. So d square by 4 is taken common, then half 2 sine theta cos theta is sine 2 theta. So this is the cross-sectional area. Now what is the weighted perimeter? Very simple. Weighted perimeter is 2 theta into r. S, this arc is the weighted perimeter. So r into, that means d by 2 into the angle subtended by the arc at the center, 2 theta. So this is equal to d theta. So hydraulic radius RH is A by P. So if we divide this by d theta, then we get d by 4 into 1 minus half sine 2 theta by theta. This is the value of RH. Now if you recollect the Manning's formula, where the discharge rate of discharge was given by 1 by n, a to the power 5 by 3, p to the power 2 by 3 into s to the power half. If you recollect this, and if I write this as this fashion, 1 by n, one cross sectional area I take out, then a to the power 2 by 3 by p to the power 2 by 3, that is a by p whole to the power 2 by 3, which is the hydraulic radius to the power 2 by 3 into s to the power half. Now if I replace this, I get q is equal to 1 by n. This a is d square by 4 into theta minus half sine 2 theta. So this is the area into RH, that means RH is this d by 4 into 1 minus half sine 2 theta by theta. That is RH, it is to the power 2/3, it is to the power 2/3 times the s to the power half. So this can be written taking the theta functions, trigonometric functions, with a constant, that means a k, that means 1 by n. So this d square, this d we take care, so this is d square, I am sorry, this d by 4 to the power 2/3, because this d by 4 in AP. So 2/3 plus 2, so q is equal to k, I am writing that afterwards, k into theta minus half sine 2 theta, okay, into 1 minus half sine 2 theta by theta to the power 2/3. From here we are writing it, where k is equal to 1 by n. So then d to the power 2/3 plus 2, d to the power 8 by 3, and 4 to the power 5 by 3, and s to the power half. That means taking this, and taking this, and 1 by n, if I write a constant, because this is constant for a given roughness, for a given slope of the bed, and the given slope of the bed, it is given slope of the conduit, and d is the diameter of the conduit, so this is constant. So in terms of a constant, I can write q like this. Now q full, when it is running full, will be obtained when we will give this theta is equal to pi. Then as this goes on increasing, this free surface or the surface of the liquid, so then theta goes on changing, increasing, and it will be 180 degree pi. So theta pi, you see these are all 0, so k pi. So we can write q by q full is equal to this by pi. That means 1 by pi into theta minus half sine 2 theta into 1 minus half sine 2 theta by theta whole to the power 2/3. Now we can also develop the expression of, from here we can also develop the expression of V by V full. V by V full. What is V by V full? It is Q by Q full, the ratio of the discharge, into V is Q by A. That means A full by A. What is A full by A? A full by A is equal to pi d square by 4. This is the full area, and this area is the cross sectional area, which we already developed, d square by 4 theta minus half sine 2 theta. So therefore 4 d square by 4 theta minus half sine 2 theta. So therefore, so if you cancel this d square 4, this is pi by theta minus half sine 2 theta. So if you now write this V by V full, then V by V full, if you now express A full by A with Q by Q full, then this will be cancels. This will be cancelled and pi will be cancelled. So 1 minus half sine 2 theta by theta whole to the power 2 by 3. That means a full by a is pi by this. So I write q by q full into a full by a by this equation. So q by q full is this, and this a full by a is this one. That is the ratio of full area to the area of the cross-sectional area of the liquid flow. So this cancels, so only this thing, pi cancel this. So this and this formula, that is the variation of q with the q full, that in the when v by v full is plotted not with theta but with the depth of flow, that is d or the diameter here, not depth of flow, I am sorry, with the diameter of the conduit. So what is the diameter of the conduit in terms of the theta? We can write that if this is d by 2, so we can write in terms of the depth of flow, diameter and depth. So h depth is d by 2 minus this one, d by 2 cos theta. So h by d is half minus half cos theta. Okay, I can do it in a separate page, all right? Yes, I can do it in a separate page, that if this is the, sorry, this is the center, sorry, this is not correct. I can do it in a separate page, that, so this is there. So this is the depth of flow h, and this is the d by 2, and if this be the theta, then h is d by 2 minus this one minus d by 2 cos theta. That means h by d half minus half cos theta. So taking theta as a dummy variable, we can plot v by v full and q by q full with h by d. That means generate q by q full for different values of as a function of h by d and v by v full as a function of h by d. And if we plot these results, we will get a curve like this. We will get a curve like this if q by q full and v by v full versus h by d. So let this is 1 and here it is 1. Then q by q full, it goes to 1 obviously, but it slightly, sorry, it reaches the value of 1 when it is 1, I am sorry. So it slightly, it finished. And v by v full, if we, sorry, this is like this. This is v by v full, this is q by q full. So interesting feature is that the value of q by q full exceeds 1 at some values near the top surface. Similarly, the values of v by v full exceeds 1 before the conduit is fully filled. That means we get more discharge for partly filled compared to that full flow, and we get more velocity when the fluid is partly filled but not full flow. This is because of the fact that the friction in full flow is much more compared to that in partly flow. Thank you.